Alright, so in this video, I'm going to derive the first dimensional heat diffusion equation, and in the second part, I'm going to simulate this response with a uniform rod in Excel. Alright, to start this, we have to write the energy balance. And before we even write the energy balance, we have to assume that we have some brick with thickness delta x and cross-sectional area A. Can break this sections over delta t, time. Alright, now get into the energy balance. So energy balance is energy in minus energy out equals energy stored. This relates to heat by heat in minus heat out equals the density, the cross-sectional area times the thickness times the heat capacity times the partial derivative of temperature over the partial derivative of time. So now we're finished with the energy balance. Now we have to apply Fourier's law. Fourier's law, we recall, is heat conductivity times cross-sectional area times the partial derivative of temperature over the partial derivative of distance. We can apply this to this equation and divide out cross-sectional area times thickness, and we also assume delta t and delta x approach 0. So that gives us that gives us the partial derivative of x times conductivity, partial derivative of temperature over x equals density times heat capacity over the partial derivative of temperature over time. All right, so now that we applied Fourier's law, then we can go to the constant heat diffusivity. So we assume K is constant. Therefore, we can take it out. So K is equal to the second partial derivative of temperature over the second partial derivative of distance equals density times heat capacity over the partial derivative of temperature over time. All right, so then we recall that K is thermal conductivity, and this is thermal diffusivity, and we recall that this can be calculated by K over density, thermal conductivity over density over heat capacity. We can add this into this equation, and for the final final heat equation for 1D is equal to partial derivative of temperature over the partial derivative of time is equal to the heat diffusivity of the second derivative of temperature over the second derivative of distance. There we go. So now I'm going to go into Excel and model this equation. Now I'm going to model the first dimensional heat diffusion equation. First, I am going to model my variables. Alright, we're going to set this one equal 0.4. Set this one equal 20 degrees Celsius, and to the left 50 degrees Celsius, and to the right 80 degrees Celsius. Alright, now I'm going to create 10 different heat blocks, and I'm going to go down at least 100 iterations, 250 iterations, doesn't really matter. Alright, now we're going to set 0 to equal, alright, set this one equal to the left. Sorry, I have to delete these. Right. Sorry. Alright, now set this equal to T left. Take that down, all those iterations. Set all the way up block to T right. Alright. And now set all of these equal to T initial. Alright. Now the heat diffusion equation. So I want to set this plus times over and drop it down. Perfect. All right. So this is stable. Now let's model when it becomes unstable. Let's see, 5. Still stable. 6. And we're unstable now. This is because you can't go too long with the equation with like the time variable, because then it's not realistic and not compatible. All right. Thank you.